we learned two simple ways to build models or classifiers, namely decision trees and k-nearest neighbors. Today, we'll study how we can set up experiments and evaluate and choose models. We'll also learn statistical learning theory. Again, in a supervised learning setting, we have a bunch of data that we feed into some learning algorithm, say our k-nearest neighbors algorithm or decision tree algorithm. We also have to decide what kind of features we're going to use. And the result of it is a model or classifier that we can use to classify something we have not seen before. When it comes to evaluating models, perhaps you're most familiar with these measures: accuracy and error rate. Accuracy is just the percentage of the time the model is correct, and error rate is the percentage of the time it's incorrect. The problem with these measures, though, is that they're not really useful when the classes are imbalanced, and that's typically the case in real life. For example, suppose we're trying to build a cancer classifier, and let's say 99% of people don't have cancer, and 1% of people have cancer. Now, a model that always says no cancer would have 99% accuracy and 1% error rate, but it's not useful. Somehow, accuracy and error rate don't capture how good the model is. So there are other measures that we can make use of. Unlike the accuracy and the error rate, these evaluation measures are measured with respect to a class. And when you don't specify the class, it's assumed that you're evaluating with respect to the positive class. And the positive class is a class of interest. In the cancer example, the cancer case would be the positive class, whereas the negative class would be no cancer. The columns are the actual classes of the patients, so does the patient actually have cancer or not? And the rows are the model's classification of the patients, so does the model think that the given patient has cancer or not? When the model classifies a cancer patient as cancer patient, that's true positive. When a model classifies a non-cancer patient as a cancer patient, that's false positive. When it classifies a cancer patient as a non-cancer patient, that's false negative. And when it classifies non-cancer patient as non-cancer patient, that's true negative. So using these terms, we can express accuracy as true positive plus true negative over everything. True positive, true negative, false positive, and false negative. Out of all examples, how many did the model get correct? But as we talked about, accuracy is not such a good measure when the classes are not balanced. So we'll look at three different measures: precision, recall, and F1. Precision is the true positive over true positive plus false positive. So this literally captures how precise the model is. If the model says the patient is a cancer patient, what's the probability of that patient actually being a cancer patient? Recall, on the other hand, is true positive over true positive plus false negative. So out of all cancer patients, what percentage were identified by this model? An F1 measure is the harmonic mean of precision and recall. And since the harmonic mean is always smaller than the arithmetic mean, you can say that this is a more conservative measure. And the equation for that is 2 times precision times recall over precision plus recall. And a more general version of F1 measure is F beta, where the equation is 1 plus beta squared times P times R over beta squared times P plus R. And beta here could be as small as 0 and can go up to infinity. And when you plug in 1, that's how you get F1. And when you plug in 0, so F of 0 is just PR over R, which is P. And when it goes to infinity, it's the opposite effect, so it becomes R. So the beta value determines whether the precision is being weighed more or the recall is. Now we're going to look at something called cross-validation, or how we set up experiments. Suppose we're trying to build a cancer classifier. We have everyone in the world. And obviously we can't afford to use everyone's data to train our classifier. So we randomly draw from these people to come up with our data set. And the data set looks like this. We have vector representation of each patient. So suppose our first feature is this person coughing? Does this person have a fever? True. Does this person have sore throat? True. Does this person have runny nose? Maybe false, and so on. So that's our vector representation of our patient. And then y1 would tell us whether this person is a cancer patient. Say true. So we have a whole bunch of these pairs of x's and y's. And with this training data, we can build a variety of models. And with this training data, we can build a variety of models. The resulting model depends on our choice of features, which learning algorithm we employ, which hyperparameters we use for the given learning algorithm. For example, if we're using k and n, which k are we using, and what's the similarity measure we're using, and so on. And suppose we have p such combinations of learning algorithms and features. Now we want to check which of these is the best. And it doesn't really make sense to use our training data to test our resulting models, because these models were trained using this training data. So we want to test these models using some data that we didn't use for training. And let's call it validation set. So we have these models and we test them on our validation data using some evaluation measure. And this evaluation measure could be, for example, F1. Once we evaluate all the models, we'll know which model performs the best. And this in turn means we know which learning algorithm, feature, and hyperparameter combination gives the best result. Using this setting and both the training and the validation data, we train our final model called H-final. And we use both training and validation data because typically the more data you have, the better performing your classifier is. So now we have a model, H-final, but before we can use this, we want to have some sense of how reliable this thing is. And we can't use the training data or the validation data to test this because those data sets were used to build this thing. So we have a whole new data called test data, and we test H-final on the test data, and that is the estimate of how reliable our model is. And ideally, this should happen only once. If you do this more than once and keep changing up your feature set and learning algorithm choice, then your test data is basically your validation data. So this performance won't be a good estimate of how well the model will perform in the wild. It's an exaggerated performance. In the process we just went over, we had separate sets for training and validation. This is called holdout cost validation because you're holding out the validation set when you're training. And typically people use 7 to 3 or 8 to 2. So you train using the training set and you test it on the validation set to finalize your design choices. And this whole thing becomes your training set. This is fine as long as you have enough data. But when you don't have enough data, what could happen is the validation set becomes so small that it could only have a specific type of examples. So maybe your validation set only consists of people with runny nose. Then the validation set is not a good representative of the real population. So when you finalize your design choices based on this validation set, it may not work well in the wild. So when you don't have enough data, you can do what's called k-fold cross validation. Typically k is 3, 4, or 5. The train to validation ratio would be 2 to 1, and 3 to 1, and 4 to 1. And the way you do it is this. So suppose we do 5-fold cross validation. So you divide your training and validation set into 5 groups. And in the first run, you use the first 4 as the training set, and the last one as the validation set. And you repeat the experiment, but now you use the 4th group as the validation set, and the rest as training. And the third time, you use the 3rd group as the validation and the rest as training. And you repeat this 5 times and take the average. So this way, you're using every data point as validation, so you don't run the risk of the validation set only consisting of, say, people with runny nose only. And as you keep training and evaluating the models, your performance in the training data is likely to go up, because you're modifying your design choices to maximize this value. But if you consider the performance on the test set, it would go up initially and then start degrading. Because after a while, you're likely to make decisions that are too specific to your training set. For example, in your training set, it happened that someone with last name starting with X has cancer. And suppose you use that as your feature. Then in your training set, your performance improves, but obviously this is not a useful feature in reality, so the model will not perform well on the test set nor in the real world. And that's called overfitting. And when your model is not expressive enough, it's called underfitting. So the sweet spot you're targeting is right here. The issue of overfitting is typically handled by balancing accuracy and complexity. So suppose we have the red dots as data points, and we have two models, the blue model and the green model. And as you can see, the blue model gets everything correct, whereas the green model misses 2 data points. So in this case, if you just consider the accuracy, then you might be tempted to pick blue, but it's likely that the 2 data points I circled are noises, and perhaps the green model is a better model. By imposing some limit on the complexity, you could end up choosing the green one over the blue one. Regularization is how you impose the limit on the complexity, and the underlying principle is the Occam's razor we talked about. And examples of regularization would be reducing the number of nodes in decision trees, or using the p-norm as a penalty in our models. So we studied how to set up experiments and evaluate the models to pick the best one, but in real life, it often is the case that using an ensemble of multiple models does the best. So let's look at how you do this. So the idea behind ensemble learning is to have multiple classifiers, and the final prediction is based on these predictions. So instead of having a single classifier, we actually have 4 classifiers, and the output of H is based on the output of H1 through H4, usually majority vote. So if you look at, say, the first data point, like this one, H1, H2, H4 got it correct, whatever the right classification is, and H3 got it wrong. So if you took the majority vote, the output of H would be the correct classification. And you can also give more weight to wrongly classified examples, so that the classifiers that correctly classify difficult examples are weighed more in the voting process. On the left-hand side, you can see that as you increase the training set size, the performance increases overall. On the right-hand side, as you increase the number of models that form the ensemble, you see a steep increase in performance, but after a while, it plateaus. A real-life example of ensemble learning doing well is the Netflix Prize from 2009. Netflix had an open competition to build the best performing recommendation system, and the evaluation measure they use is called root mean squared error, which literally is the root mean of squared error. Suppose y hat is the true class and y is the predicted class. Then the root mean squared error is, so you compute the error by subtracting y hat from y, and you square it, and you take the mean, so you sum it over all n examples and divide it by n, and you take the root of it. This is root mean squared error. There was a $1 million grand prize for 10% drop in root mean squared error, or $50,000 for the best performing model each year. And it began in 2006 and ended in 2009. The dataset consisted of 100 million ratings from 1 to 5 stars, from 6 years of data, 480K users, and about 18K movies. And the test data consists of 3 million ratings. The training to test ratio is really skewed, but it's fine when you have this much data. And just to get some idea of what the data looks like, here are the movies that were rated most often. And here are the users who rated most often. So the top user rated 18,000 movies. And here's the leaderboard. And I want you to focus on the winning group's name. Belcore's Pragmatic chaos. Can you spot other team names that contain similar words? Pragmatic theory, Belcore and Big Chaos and Belcore. So what happened is, I guess these two groups formed an ensemble, and then maybe these two also formed an ensemble. And then you actually have some group called the ensemble. So this is a real-life example of how ensemble systems tend to perform better. Let's talk about some statistical learning theory. Suppose we have a fair coin. It's a coin that has 50% chance of getting tails. The question is, when you actually do an experiment, how far off from 50% can you get? So suppose we flip the coin 100 times. And since it's a fair coin, you expect 50 of these to be tails. One experiment is 100 flips, and you repeat this experiment 1,000 times. And out of those 1,000 times, the farthest off you can get from 50 was 66. So you had 66 tails and 34 heads. And when you did the experiment 10,000 times, the farthest you've gone is 69. 100,000 times, 70. And suppose when you did this 1,000,000 times, suppose you observe 74 tails in one of these experiments. That's quite far off from 50. But if you do more flips in each experiment, you become less likely to see such an outlier. Suppose you do 1,000 flips per experiment. So now you expect 500 out of these to be tails. When you repeat this experiment 1,000 times, the farthest you got from 500 is 564. 10,000 times, 564. 100,000 times, 569. And 1,000,000 times, 579. It's far below 740. And if we increase the number of flips per experiment even more, even if we repeat the experiment 1,000,000 times, the farthest you can get away from 5,000 is 239. So the takeaway is, as the data size goes up, the less likely it is for you to see an outlier. So the question is, for our classifiers, how big of a data set is big enough so that it performing well on some test set is not a fluke? So for this, we introduced a notion of probably approximately correct, or PAC learning. And here's what we want. We want to be able to prove that we can find a hypothesis H, which again is a model or classifier that's approximately correct or identical to the target F with high probability. And the underlying principle is that if our model gets a significant number of examples correct, then it's unlikely to be very wrong. What we just talked about can be formally expressed as our model H lies in the epsilon ball with probability greater than 1 minus delta. So we want to say our H falls within here. So F is a true model that would always correctly identify cancer patients, and we want to be able to say H is close enough to that. So it's within an epsilon ball with some small epsilon. And everything outside of it we call H bad, or bad hypotheses. So say we might have a really bad hypothesis here. So HX is always classify as cancer. And H is the entire set of possible hypotheses. So the first part of this formal statement, H lies in the epsilon ball, is the approximately part of PAC learning. So we're not requiring H to be exactly F, but we want it to be approximately correct. So we want H to be close enough to F. The second part of this statement, with probability greater than or equal to 1 minus delta, is the probably part of PAC learning. So we want H to be in this epsilon ball with some high probability. Note that H here is a set of all possible models, and it's based on your design choice. Say, if you define fewer features, then your space will be smaller, and if you define a lot of features, then your space will be big. And you might think that having a small h will be beneficial, because you have fewer models to explore. But if your h ends up being too small, say you have an h that's like here, you run the risk of everything in the space being really far away from f. So you have no chance of training a model that's probably approximately correct. So we want our hypothesis space H to be big enough to contain F, or have something close enough to F, while being small enough that we don't have as many models to test. The question that PAC learning can answer is, what is the number of examples that we need to find a PAC H? So to be sure that our model is probably approximately correct, how many data points do we need? Again, the more data points we have, the more sure we are. But is there any specific number? H is PAC if the error is less than epsilon with probability greater than 1 minus delta. So then, what is the probability of some bad hypothesis, correctly labeling n examples by chance? Is there some upper bound in this probability? Well, first of all, the error of H is greater than epsilon, because we're assuming that H is a bad hypothesis. So then the probability that H agrees with one example is less than or equal to 1 minus epsilon. So basically H has over epsilon % chance of misclassifying an example. So the probability of it classifying an example correctly would be less than or equal to 1 minus epsilon. Now the probability of H agreeing with n examples would be less than 1 minus epsilon to nth power. So it's less than 1 minus epsilon for each example, and you have to do that n times. The probability of any H in H bad agrees with n examples is less than or equal to the number of bad hypotheses times 1 minus epsilon to nth power. Suppose we have 3 bad models. For the first model, the chance of it getting n things correct is less than or equal to 1 minus epsilon to nth power. And for the second model, same thing, 1 minus epsilon to nth power. And for the third model, again, it's less than or equal to 1 minus epsilon to nth power. And the probability of any of these 3 models correctly classifying the n examples would be the first model or second model or the third model. So it's just 3 times 1 minus epsilon to nth power. And H bad, the number of bad models in our hypothesis space, is strictly less than the number of hypotheses. So this is less than H times 1 minus epsilon to nth power. So the probability of some bad model getting n things correct by fluke is less than or equal to the cardinality of H times 1 minus epsilon to nth power. And the probability being greater than equal to 1 minus delta is the same thing as the probability being less than or equal to delta. So then we want this value to be less than or equal to delta. And our question is, what is n that would make this happen? Again, we want to find n for which this is true. And for this, we're going to make use of the fact that 1 plus x is less than or equal to e to the power of x. And if we plug in negative epsilon in place of x, we get 1 minus epsilon is less than or equal to e to the power of negative epsilon. The left-hand side of what we're trying to show is the cardinality of h times 1 minus epsilon to nth power, which is less than or equal to the cardinality of h times e to negative epsilon times n by this. And we want to show that this new expression is less than or equal to delta, which in turn will show what we want to show. And after this point, simple math. Take natural log on both sides. And then we move natural log of h to the right-hand side. And we divide both sides by negative epsilon. And don't forget to flip over the inequality. And we distribute the negative sign where this term is the same as natural log of 1 over delta. So what does this mean? Well, n increases as epsilon decreases and delta decreases, and the cardinality of the hypothesis space increases. So that means the number of examples has to increase as you want your model to be more accurate with higher probability, and when the hypothesis space is larger, which all makes sense. So theoretically, we could have some lower bound on the number of examples that we need. But in practice, people will just get as much data as possible and just work with that. We briefly talked about how increasing the number of features increases the hypothesis space. But to get a better idea of this, let's consider a simple example. If a function maps from domain X to range Y, that means for every value X in domain X, there exists some value fx in Y. Then how many possible Boolean functions are there on n binary attributes? So Y is a set true or false, and X is a set of all vectors with n rows where each xi is either f or t. So then how many possible Boolean functions are there? Which is just the cardinality of h. Well, if there are n binary attributes, then there are 2 to the n unique data points. And two functions are different if any of these 2 to the n data points are mapped to a different f of x. And each function could map each data point to true or false. So we have two options for each data point. So it's 2 to the power of 2 to the n. So again, this comes from the fact that this is a Boolean function. And this too comes from the fact that we have binary attributes. So as an example, suppose n is 3. So each data point is represented by a 3-dimensional vector. And so we have 2 to the power of 3 data points. And for each of these data points, the model can output 0 or 1. H1 and H2 are different models because they differ in output in at least one of these data points. And function can map each data point to either 0 or 1. So there are two choices for each data point, and there are 8 data points. So you have a total of 2 to the power of 8 models. Or 2, 2, 2, 2, 3. Okay, staying with the same example of Boolean functions. So how many data points do we need to find a packed H? This is what we derived. And this thing would be natural log of 2 to 2 to n, which is big O of 2 to the n. So even for simple Boolean functions, we need exponentially many examples with respect to the number of attributes or features. And we actually saw this last class when we were discussing the curse of dimensionality, where even after adding just one feature, our space goes from 2D to 3D, and the same 8 examples no longer cover the space as well. Lastly, we'll discuss something called VC dimension. VC dimension captures the capacity of a hypothesis space. The bigger the VC dimension, the more expressive the hypothesis space is. And it's defined as follows. A hypothesis space H has VC dimension of n if for any n data points with arbitrary labels, there is some hypothesis H in the space that can correctly classify them. For example, the VC dimension of set of all linear classifiers is 3 because you can take any 3 points and label them however you want. There's always a way to classify them between positive and negative. But if you have 4 points, you could have a situation like here where there's no way to have a single linear classifier that can correctly classify them.